Okay, so we have two papers this week. Both of them are on deformable radiance fields. So I'll first present this paper is Gaussian, which is physics integrated 3D Gaussians for generative dynamics, and was released last week. So first let's take a look at their results. Maybe. Okay, so yeah, so they can deform, they take 3D Gaussians and they can deform them pretty much any way they want. So they have all of these models: fracture, elastic, deformations, plastic ones. And this is pretty awesome because in the field of nerves, like before, 3D Gaussians, there wasn't much done here that was like this extensive or would be applied to any form of deformation, and most certainly not physics-based ones. Okay, so the goal of this is to have a physically accurate motion simulation given a 3GS model. And the input is a 3GS model, or they can also get the images and train a 3GS model from scratch, but with their own added regularizers that will help with a little bit with the quality of the motion later. And the output would be the physically grounded motion synthesis. So you can see like the very general overview here. They have a 3D Gaussian trained with the regularizer that I will talk about optionally, and then they will integrate this mechanic continuum inside the Gaussians to get this dynamic effect to be able to deform this through time. And they can also adapt it to be applied to the Gaussian covariance and the spherical harmonics. And they will get the results that they will. So a quick review of 3D Gaussians is that they represent the scenes instead of like having a neural network represent the scene as a color and density field. They represent it as a set of 3D Gaussians. These Gaussians have a mean, a opacity here shown with sigma, the covariance, which is here A, and the spherical harmonics coefficients to represent the color. So then after they have these 3D Gaussians defined, they can splat them into 3D for rendering, and the splats are then alpha blended together to get the color of each pixel. And this is the alpha blending formula, which is similar to NERF's alpha blending formula. The only difference is that it's applied to the 2D Gaussian splats opacity. So after this, the scene can be trained with the photometric loss between the rendering and the ground truth image. We can also do a quick review of continuum mechanics. So continuum mechanics describes motion by a time-dependent continuous deformation. So we have a set of positions, and each time that we want to know the positions at that time, and we can deform it to get a deformed space using this function. So it goes from the undeformed space as at time 0 to the deformed space at time t. And the local transformations or the deformation gradients are shown here with F, which is the gradient of or the Jacobian of the deformation function. So there are two main laws that should be followed in continuum mechanics. And that's first, conservation of mass. So if you look at each area in the space, small area in the space, the sum of densities or mass there should remain the same after the deformation. So if you have the deformed space transformed back to the rest space, the sum of the densities should remain the same. And we also have the conservation of momentum, and that is if we have mass times acceleration, or here density times acceleration, that would be the sum of external forces and internal elastic forces. So sigma here is the Cauchy stress tensor that is defined in this way. So here the psi function here is a function of the deformation gradient that maps the deformation gradient to elastic energy. And it can be modeled with different elastic energy models. For example, the Neo-Hookean model is the, I guess, the simplest one, which you've probably seen for springs. The deformation gradient can also be further decomposed to elastic deformation and plastic deformation. So elastic deformation is the deformation that when you apply to an object, it can go back to after deformation, it can go back to the rest space. But plastic is when you pass a certain threshold and the deformation that you've applied will change the rest shape itself. So for example, you can think of punching a metal thing. For plastic, that would change the rest shape. But for elastic one, if you have a squishy thing, it can jump back to the rest shape. So any questions so far?
Sounds good.
Okay. Okay. So here they want to apply continuum mechanics to 3GS, and they have they propose to use the material point method, or MPM model, to this problem, and that's because of two things. First, we want to have these two rules followed. So the conservation of mass is easy because if you just apply to the point cloud points and deform them, you will always adhere to the mass conservation. But for the momentum conservation one, it's easier if you have a Eulerian representation, like a grid that defines a confined space where you can analyze the inside the energies changing in the confined space. So you can analyze the forces applied to that space or the change of energy inside. So we don't have the grid in the 3GS, but you have the particles. This MPM model tries to solve this with using both the grid and the points. And the process is consists of 4 steps. So you first have to define a mapping from the points to the grid nodes and vice versa. So this mapping here is done using like interpolation kernel. And then at the second step, you can just transfer the current mass velocity from the points to the grid. And then because you have the grid cells now with their velocity and mass, you can use this the forward Euler function here that is easily applied to a confined space on the grid nodes. So you can update the velocity, get the velocity of the next step, and then use the inverse mapping to transfer back the velocity to the particles and update their velocity position and other characteristics. Okay, so looking at each of these steps, so they first do the mapping using a cubic B-spline kernel that they show with this WIP. WIP is the mapping between the grid node I and particle P here. And then they transfer the mass and velocity from points to the grid. So they use the mapping for the mass mapping the mass to each grid node. And for the velocity, they also do the same, but they do a first order approximation of the velocity at the grid point here using this affine momentum. So the affine momentum, you can think of this this formula here as a first order Taylor expansion to find the velocity of the grid node, given the expanding the term around the particles velocity. So they can find this momentum and mass at each grid node. So after they have it on the grid node, they can just do forward Euler using the same formula as before. So here we have mass times acceleration. For acceleration, we have this numerical approximation of it between two times. And then here we have the energy function, the elastic energy function for finding the Cauchy tensor, the mapping, and the external force that the user can apply. Yeah, so this will give you the next steps velocity at grid points. And further, this V0 here is the rest volume. Sorry, it's the volume of the rest volume of the grid cells, which is calculated as the number of the density, the user-defined density of the material divided by the number of particles that fall into that grid cell. So after you find the next step's velocity, you can transfer it back to the particles and find their next step positions and velocity. So here's the transfer back formulas. I won't go over all of them, but it's just the mapping for the velocity, the B-spline mapping to the points, and then the usual update of the positions. You can also do it for the deformation gradients and so on. One thing that is important here is this F of plastic. They can use different like models for the plastic deformation gradient. And they show like the different models in the supplementary, so they can get like better fracture and stuff like that. And this tau here is just another notation they use for the same psi that we saw here as the hyperelastic energy. Okay. So, any questions still here? Okay, so till now it's mostly like you have a point cloud. You have a point cloud and you're just deforming the point cloud. It's not doing anything for the Gaussians. So to account for that, they say that, okay, if we apply the deformation function that we found so far to the points, like the inverse of it, the function that we get would not be a Gaussian with respect to x anymore necessarily. So instead, they do a first order approximation of the deformation and do a simple affine transformation on and assume a simple affine transformation on the points. So here is just a rotation and translation, and they apply this affine transformation for their covariance matrix. So still a because it's a linear transformation, it's still a Gaussian. So other than that, for the color, if you look at the first figure here, when they rotate or for example, when they deform this shape here, the color will not deform with it, so it doesn't rotate here. You should see like blue here, but you'll see this orange color. So they can rotate the spherical harmonics if they rotate the basis functions, but because like the basis functions are not are fixed during the training of 3GS, they just rotate the view direction instead. And then they do two other tricks that these two are optional to train their 3D Gaussian better. So it looks better in the deformation application. So first one is that so when you train 3D Gaussians, mostly the Gaussians try to fill the surfaces. And they don't have a really volumetric, they're in a sense not really volumetric. The Gaussians will mostly just fall on the surfaces and the inside is mostly empty. So to fix that for like physics, we don't want the insides to be empty. So they take a grid, and for each point in the grid, for each node in the grid, they look at the 6 axes. And if the sent out rays from the node hits a surface 2 times, like 2 out of the 6 hit a surface, then they assume that that point is inside a object, and they assign the Gaussian closest to it to that grid node, to that point. And yeah, so they fill the Gaussians this way. And another thing that they do is that they regularize the Gaussians so they're not so thin. So again, the Gaussians that you usually get are both on the surface and are very thin in 1 or 2 dimensions. So if you look at them from like the views that are not seen in the training views, you'll get spiky noises sometimes. And when you deform them, you can get the spiky noises from many views. So they instead want this Gaussians that are learned to be not so thin and spiky. So they use this regularizer that tries to minimize the biggest to the smallest eigenvalue of the Gaussians. Or the scales, yeah. So the same thing. So the smallest eigenvalues and so small, and the Gaussians are in T. Okay, so here are some results from their comparison to other methods and some of the ablations. So For comparison, they use their own data set that they use a lattice deformation on these objects to get ground truth, and then use PSNR scores to get metrics between the simulated and ground truth deformations, and they do better on all of this. So the three baselines that they compare to, the first two transform nerves to meshes, from what I remember, and then apply deformation on meshes. TAC nerve, I think they transform nerve to a point cloud type of thing, or a point-based representation, and then does the deformation. But theirs is better. I think most of it comes from the factor that they're both physics-based, and like 3GS itself is better in quality. And so this shows it better. So for example, nerve editing doesn't have any physics-based any physical awareness. So when you like try to stretch this, it completely like the mass conservation is not passed here, while there's does a better job. And these are the like the optional steps. Like without the internal filling, we'll get like this squishy thing because there's no mass inside these globes here. And the regularizer also like helps solve these spikes here. They did not report really how this regularizer affects like 3GS quality itself. They just showed it for deformation, but that would be interesting. And I think that was all. Look at some other results here. Yeah. They have more like on the math side of how each of these are modeled in their supplementary, like the energy functions different and the plastic decomposition is different. I didn't go into them. You can refer to the paper for like, if you're interested in that. But it was like regular common function models for these. I think what their method really establishes is a very general way of applying whatever physics model that you have to 3D functions, which I find cool. Any questions, comments?
Wait, so they define different energy functions for each model?
I think they define different plastic decomposition.
Oh.
But they also like investigate how each of the energy models fits into their models, into their method in the supplementary.
You can't really apply this to anything.
Mhm.
So you can't really apply this to anything, like neither of the energy function.
Why not?
I mean, they're categorized in energy functions, right?
Yeah. Yeah, you cannot like directly apply it to everything. But I think that's common in simulation. You have to set some different modes. Yeah, they have this like analysis. Okay. Go to the next paper. So Harshit, will you come here? Yeah.
Okay, so our paper is drivable 3D Gaussian avatars. Our objective is to deform the Gaussians so that we can get fast rendering. So this is trained on just humans. So we'll have 3 MLPs for 3 things: one for face, one for body, and one for garments. The first one, phi, is it will take a pose and the vertex of each vertex of tetrahedron, and then it will define the uh, vertex of offset. Pi will take pose and the barycentric coordinates rotation scale for Gaussian defined in tetrahedron, and then it will find the offset. Gamma would take pose, view, and the features for each Gaussian and would give you color and opacity. So can this, yeah, okay. So we have our what vertices. We use our MLP to get the offset. We change the vertices. Then we use pi to get the new Gaussian coordinates and the deformation for Gaussian, and we apply it to each tetrahedron. Then for gamma, we have our view and the features, and we use them to get the color and opacity. So this, yeah,
Where do you get the features from?
they use auto decoder, I think.
Oh, out of the chef one.
Sorry,
You trained that from scratch, or it's a pre-trained of the coder?
I can't hear you.
Yeah, I mean, is it a pre-trained autoencoder?
What's the question?
Yes, do they train it?
There was no mention of it. I think, yeah, they use all, like, I think they train it, yeah. Train to get the features, yeah. Okay, so when we get our color, we segment the model into parts. Each part would have a constant color. And this thing is used for garments. And we then use the color and opacity to render the final model. So for garments, this is our usual this is the way to render the colors, right? So we change CI with our parts color, and for each pixel we render the part. And for garment, we take L1 loss between P bar and P. So with garment loss, the garments don't blend into each other. That's the thing. Okay. So this one is for deformation of tetrahedron. We don't want them to stretch too much and distort too much. So JI is the change in transformation. It's the matrix which defines the change in transformation for a tetrahedron. And the first term is for compression and expansion, and the second term is for distortion. Then we have usual 3D Gaussian laws, and then we add all of them up to get the final loss. Yeah. So results, they use 2 methods for mesh. One is LBS, the other one is FFT. Except for this one, their method performs the best. They didn't give much reasoning on why this performs the best. Okay, yeah, that's all. Sure. This one. This one?
Yeah. Yeah. So
Oh, so they use 3 MLPs for each face, garment, and body. So the first MLP is for change in vertex, like the offset. The second one is to second one defines the offset offset for Gaussians within tetrahedron. And the third one is for color, and it defines the color and opacity. And we do this for each face, garment, and body.
So, how is the pose defined?
I think this is the paper open. Sure. Mm,
Not sure. I think probably they did something like the pose for,
like this paper has a lot of missing details. I couldn't find like what's this F for? Like they didn't write it all. Like, what's this F?
oh, joy angles. Yeah, so I think they use as a real.
Yeah.
Well, I'll just see it. Here. I don't know what they mean by it.
Yeah, they don't even explain what's F like. Mm.
Thank you.
Yeah. Interesting that they just output the like they just output the rotation and everything here.
And so, the networks are trained on some data they have, or what's that?
Yeah, I think
Or
it's
you
a
listen on-
video.
Really haven't captured it all.
It's a video, I guess.
Oh, I see.
Yeah.
So it's Christian Theobald.
Sorry?
This is the typical MPI data set.
Yeah,
Christian Theobald.
yeah. I think they're fitting to a video. It's not like the previous one. They were simulating. Yeah. Yeah. Be interesting to see how it's like compares to the 4D Gaussian thing. Okay. I think that concludes it for today. Stop.